Hello again. We are done with chapter 10 and we're going to start chapter 11. So let's go to the lecture. Simulation model, part 1, chapter 11. So what we have done for simulation so far has been introduction, or just introduction as the name suggests, and simple rather. So we're going to dive deeper and study and investigate more advanced problems. So let's start with kind of a scheduling problems here that may kind of be familiar to you or rather help you in your daily life. The scheduling dental patients. So in this problem, we assume that there's a physician, there's a doctor, dentist who wants to schedule these patients. And so the schedule is done in advance. Suppose that we have like 8 patients, as you can see here in this table, and they're listed by just random numbers, random letters, A, B, C, D, F, G, H. The scheduled appointment time are shown in the second column. So the physician starts at 9:30 and he's supposed to take a flight at 12:15. But if he has a patient, he cannot just leave the patient at the end. So we're gonna, in this problem, we're gonna see based on the source of uncertainty which is how much when and if a patient would arrive to office and how long his or her test or exam is going to take. We're going to see, we're going to kind of run this simulation to figure out what is the probability of this patient, this dentist, this physician gets into his flight, takes his flight, based on the source of uncertainties that we have. So you can see the scheduled appointment time for A is 9:30 a.m. And for B is 9:45. For C is 10:15 a.m. So as you can see here, each patient actually requires different kind of tests, which would take different times. The estimation for the exam time are shown in the last column in minutes. For example, A would take 15 minutes, his or her exam. The B takes 20 minutes, C takes 15 minutes, so on and so forth. But because the exam times kind of varies, we have kind of some slacks here. That means that there are times in this schedule, at least, that the physician is vacant, is not working. For example, we see that for patient B, the scheduled appointment time is 9:45 and his or her exam takes 20 minutes. So the physician would be done by 10:05, and the next patient is scheduled as 10:15. So there's going to be a 10 minutes slack. We also have that for D, and also the last one. For example, the last one is scheduled as 11:50 and his exam takes 15 minutes. So the patient will be done by 12:05, but the physician has to leave for his flight at 10:15. So there's like 10 minutes of slack here. Okay, so there are 2 sources of randomness and scarcity here. One is the patient arrival time, and the other one is the actual exam time, and that means how long the exam takes for each patient. We have to kind of come up with the distribution as we have done so far for simulation, or the source of uncertainty. So for these 2 sources of uncertainty, we have these 2 probability distribution. For the arrival time, a patient can arrive 20 minutes early by a probability of 10%. So there is a 20% chance the patient comes 10 minutes early. There are 40% chance that the patient comes exactly on time. There are 25% chance that the patient would arrive 10 minutes late, and 5% chance the patient would arrive 20 minutes late. For the exam time, as you can see here, there is a 15% probability and chance that the exam lengths would be 80% of the original assumed times. And 50% chance that the exam is going to take exactly as they supposed to take. And there is 25% chance that it's going to take 20% more, or 1.2 multiplier. And there's a 10% chance that the exam would take 40% more than it is supposed to. So the multiplier is 1.4. So there are some assumptions in this model. First is the dentist, Dr. Gordon, is ready to start treating patient at 9:30, as we mentioned before. The second assumption is that the patients are treated in orders that they are scheduled exams, even if they are late. So if they're late, they have to be taken care of even if they're late. And the third assumption is that the appointment can start early if the patients and Dr. Gordon are both available. So the question that we want to investigate is, will Dr. Gordon would finish treating all his patients by 12:15 so he can leave at 12:15 for his flight, based on these uncertainties that we have. So we're gonna model this problem again using Excel. There are no decision variable in this problem. It's just an output actually. So we want to see the probability, the possibility, the chance that Dr. Gordon would be able to take his flight. So we're going to run several replications, say a couple of hundreds, to see what is the chances that he would be able to take his flight. We could actually kind of change this model to find the time by which he has 80% or 90% chance of finishing and being able to take his flight. So as I mentioned, there are several, actually 3 main assumptions in this model. So all models, especially simulation models, have to make assumptions to be able to, for us to make the problem simple to be able to model it. But here, the second assumption actually makes the model easy enough for us to build it in Excel. And this is kind of a single server queuing system that we talked about in the previous lecture. For a more complicated problem, such as a multi-server problem, we can't actually model those problems in Excel. So you're going to have to use more sophisticated softwares. Okay, so let's go and get started with the modeling. So I'm going to open up the Excel file, the simulation sim models dentist. It's going to take a few seconds to be able to open it. Okay. Let me share this with you. So here you can see actually that you can see the data. Sorry. So the inputs are shown in this table. For the 2 sources of uncertainty that we have, which is the patient's arrival time and the schedule, the exam length, we have the inputs here. These are the list of patients that we saw in the slides. So patients, we have 8 patients here, A, B, C, D, E, F, G, H. These are, the second column shows the scheduled appointment time, and last column shows the estimated exam length. So These are our estimations. Of course, there's source of uncertainty, two sources of uncertainty. One is the patient's arrival time, and the other one is the source of the exam length. So these two are going to be random variables. These two probability distributions shows the probability distribution of the two sources of uncertainty. So, for example, this one shows for the arrival of patients. These distributions, as you can see here. So, for example, this is actually the cumulative probability distribution. So there is a 10% chance, according to the lecture slide that we have, there is a 10% chance that patients would arrive 20 minutes late. There is 20% chance that patients would arrive 10 minutes late. 40% of the time, the patients are on time, 25% 10 minutes late, and 5% 20 minutes late. Okay, so 10% 20 minutes early. To modify my statement, 10%, there's a 10% chance that the patient is 20 minutes early, 20% that 10 minutes early, 40% on time, 25% 10 minutes late, and 5% 20 minutes late. So based on this information, we can actually come up with this distribution here that you can see, cumulative probability distribution. So for example, you're going to start off with 0. So that's 20% early. So that's why 20 minutes early. So that's why we have minus 20, because that's early, right? So 0 early. For the next row, we're going to add up 0 here plus the 10%. So that would be 10% more. And that would be the probability of cumulative probability of 10 minutes early. So that's negative 10 here. So the next one is on time. So there's 0 slack here. And the probability here would be to add up the previous one, which is 10 plus 20 here. So 10 plus 20, that's 30. So 30%, 0. And for the next one, again, we're going to add up the 30% and 40%. So it's going to be 70% of time, 70% chance that we have 10 minutes late. So 10 minutes late is going to be adding 10 minutes, right? So that's plus 10 here. Okay, so 70%, 10 minutes plus 10. And the next one is going to be 70% plus this 25%, which is 90%. And this is going to be for the case that we have 20 minutes late. So that's plus 20 here. Okay. So the first column shows the cumulative probability, not exactly cumulative, just for the real VLOOKUP table. And the second column shows the early or late arrival. The next shows for the other random variable, which is the exam length. So, for example, we had 15% chance that the exam would take 20% less or finish 20% earlier, 50% chance that it would take exactly as what it was estimated, 25% chance that there is 20% more than it would take. They thought that it would take. 10% chance that it would take 40% more, or 1.4. Okay? So we're going to build up this probability distribution similar to what we had here. This is cumulative probability distribution. We're going to start off by 0 for 80%. So 20% less, that means 100% minus 20. So that's why this is like 80%. So I can actually change this to percentages so that it will be familiar to you. 50% on time. So there is 100. The exam length would be 100% of it, what it was estimated. And it is 120% for 25% of the time, but the cumulative probability are going to be similar. So we're going to start off by 0, then 0 for the next row, it would be 0 plus 15%, so that's 15%. For the next row would be 15% plus 50%, so that's 65%. For the next row, it would be 65% plus 25%, which is 90%. Okay. All right. So the first thing that we're going to need to do, I'm going to have to name actually these. So I'm going to call these and name these the ALF. ALF, that's arrival lateness factor. And I'm going to call this data the ELM, or the exam length multiplier. So now I can use them in the formulas. Okay. So now that we went over this distribution, these two random variables, let's go to the rest of the model. Okay. So this is how we want to model. We have the list of patients here, A, B, C, D, E, F, G, H, the scheduled time. So basically, this is the copy of this table here that we had in the lecture slides. And the rest of these are the computed values that we have to do, and also some randomness here. So for example, the next column shows the arrival lateness factor. So the arrival lateness factor is actually a random variable here. So it has to be kind of the green style here that we have to use. We have to use the green style here. So I'm going to use random style here. And let's actually do that. The arrival lateness factor, we're going to sample from this table here. Okay, so I'm going to use the VLOOKUP. And I'm going to generate a random number using rand function. And then I'm going to give it the table, this table. You can just select it or just say, or say, now I want you to give us these factors here. So it's going to generate, give us return the second columns plus values. So right now is 0. So it gave us this one. That means the probability was within 30%. Okay. The actual arrival time. So the actual arrival time is the estimated arrival time, the scheduled time, and the arrival lateness. So it would be, it was supposed to, it was estimated that patient A would arrive at 9:30, and the arrival lateness factor is 0. So that means it's going to come actually exactly at this time, right? So this is what we want to say. So this is going to be, as you can see here, based on minutes. Okay, so these are minutes. Okay, so now it's 0 minutes. So what we have to do for the arrival time here, I'm going to use actually the timing here. So I'm going to say this scheduled time here plus plus this is the minutes. So because this is like time type data, I have to convert this to in time as well. So I'm going to use the time function, and it has 3 actually parameters, as you can see here: hour, minutes, and seconds. Because we don't have any hour here, so I'm going to leave 0 here. And for minutes, I'm going to give it this value, the random values. And for the seconds is also 0. So I'm going to close that. But this is only when we have adding up. Okay, so what if we want to kind of we have earlier, would arrive earlier. So for that, we have to also do that. So let's, because the time function doesn't have that negativity here, so we're going to say if the arrival factor here, which is D40, D40 is greater than 0, greater than equal to 0, then do this. Otherwise, if it's false, then do the B40 minus time over 0, then negative this value, which is D40 again. D40. Seconds are 0. So now, if it's negative, then it's going to put this negative value in that value, because it doesn't take actually negative. The time function doesn't take negative parameters. So that's why I added this negative here. Then D40 is negative. Okay. And it would take it, it would make it as a positive value, kind of like an absolute value. And it would deduce it from B40. Okay, so it would actually compute the early time. So right now, for example, it would be the estimated time is 9:30 arrival. It has 10 minutes late factor. So the exact arrival time would be 9:40. Okay, so now if I just recompute this, we're going to get different values here. For example, I want to look for a negative value. Okay. So for example, for negative value here, the arrival lateness factor is 10 minutes early. So that's -10. So it was estimated to arrive at 9:30, but it is arriving 10 minutes early. So that's 9:20 the arrival time. Actual arrival time is 9:20. So it looks like that it works fine. The time exam begins when it begins. So the time would begins would be a maximum of when the person would arrive and when the scheduled appointment time. So, for example, if the person has arrived earlier than he was supposed to, he cannot start his exam right away, right? It has to be within the scheduled time frame. Okay? So that's why we use the maximum arrival time. But if it is past the scheduled appointment time, and he is arriving late, for example, 10 minutes late, he still has to be taken care of. Okay, so that's why we use a maximum number. Right, the next one, computed value, is the exam length multiplier. This is also a random variable. The multiplier is another source of uncertainty, so I'm going to use the style for randomness here. And this is how we're going to compute it. We're going to have to, again, use the VLOOKUP function and also the rand function to sample from this distribution. So I'm going to use the ELM, and I'm going to ask it to return the factors here. Right? So it's like 1.2 or 120% here. All right. The actual exam length. Right. Let me actually refresh this cell a couple of times to see if it works, the randomness work. And I can see here it actually works. Okay. So the actual exam length would be the estimated one multiplied by the multiplier, which is the random variable, right? So for example, it was supposed to take 15 minutes, but the multiplier, random multiplier is 80%, so it's going to be 12 minutes. Another time, exactly 15%. Another time, it was supposed to take 15 minutes, but we have a 1.2, like 120%, so that's just going to take 18 minutes instead. And the actual finish time is going to be the actual arrival time plus the time that exam would begin. So it would be the time that exam begins plus the actual time that exam takes. So it would be just 2. All right. So this is interesting. For example, the scheduled appointment is 9:30 and the estimated time for the exam is 15, but the persons arrived 10 minutes early, and the estimated exam time is actually is more than was estimated. So the exact one is 80% of that. That's instead of 15 minutes, is 20 minutes. So he still would finish off as he was meant to. Right. All right. Okay. But remember that we can actually just copy these. We can copy these two. Yes, we can copy these two, for example. But we cannot copy this one because for the next patient, the time that exam begins for that patient is actually equal to the maximum of the time that the previous patient is done and the actual arrival of this person. So that if the next patient has arrived, but the previous patient is still under exam, you can't just cut it off and start a new patient, right? So you have to wait for the previous patient to be done so that the next patient can start his or her operation. Okay, so we're going to use the maximum of the actual finish time of the previous patient and the arrival time of the new patient. And we can copy actually the next 3 values here. So now I can copy all of these values for all these patients. So it looks like that is oh yeah, so you have to use, that's why it doesn't work. I have to use the time function. time function 0, 18. Okay, so it looks like it works. All right. So the last patient is actually for right now is 12:30. So here we can add another one. Would, for example, would be able to make flight, question mark, and here we can say whether or not. So if this value, the actual finish time of the last patient, if it's less than 12:15, time less than time 12:0, then you would be able to, otherwise it would be. And I'm gonna use the general value, so now it should work. Okay, so this is going to be our output. Okay, great. All right, so let's actually test the model for different values. I have to add another equality sign here. Okay, so for example, for this scenario, the last patient would be done by 12:15 exactly. So Dr. Gordon would be able to take his flight. Right. Okay, so this is just one replication. So we need to run several scenarios here. Okay, so let's do that here, for example. Replication number, that number. This is not this is not a the replication number is, for example, 1, 2, 3. And here we want to compute, for example, makes flight or not. We'll be able to make flight or not. And also, for example, suppose that we want to see the finish time of the last patient. Right? Because I want to run one-way table here, I'm going to leave this empty. And this make flight is going to be this cell, reference to this cell. The finish time is going to be reference to this cell. Okay. So now I'm going to run this for, say, 100 applications, 400 applications. 400, 400. This 400 application. And now I'm going to take all of these values and open up the data what if analysis data table. And here I'm just going to reference it to a random cell. I'm going to hit OK, and it's going to show as you can see here. Let me align this in the middle so we can be easily read. Align in center, and I want to use this format for these values. So it was shown as a time. Okay. All right. So we have replicated this experiment or simulation to 400 times. You can do it for more if you want. Now let's come up here and then come up with the summary of our experiments or simulation. So I'm gonna do it here, for example. So this is the summary of simulation. the number of replication, the probability of make flight, that's the estimation. The standard error, we want to compute confidence interval. So that would be a 95% confidence interval lower and a 95% confidence interval upper. Okay, so the number of replication is 400 here in this experiment. Line this in the center. The probability of make flight, our estimation. So this is what we're gonna do. We're gonna just find the average of all of these values. Or we could sum them up. It would be 0 and 1. Sum them up and then divide them by 400. Okay. All right. So I'm gonna convert this to percentages. 30.5%. The standard error would be, again, this is a proportion, so it would be the square root of pi multiplied by 1 minus pi divided by n. So it would be the SQRT of the pi, which is our estimation, multiplied by 1 minus this value, and then divided by this value. The reason that it produced that sounds that warning was because I didn't put the last parenthesis added automatically. So here I'm going to use the format of the previous cell for this cell as well. So it would show up in the percentages as well. Now I'm going to compute the lower limit for the confidence interval, 95% confidence interval. So that would be equal to, this is going to be actually our output cell. So this is pi, our estimation of the probability of be able to take flight, minus 1.96 multiplied by the standard error, and equal to the probability estimation plus 1.96 multiplied by the standard. Okay. So I'm going to use also this formatting for these two cells. Okay. Good. So as you can see here, you can actually, these values can change because each time that you refresh your cells is going to generate new numbers. But we run all of the experiments. So for example, the average is between 24% and 30% chance. So the probability that the Deca-Gordon will be able to take his flights based on this data that they have is actually very low. It's like about 1/3. Okay, so it's like about 30%, less than 30% that he has a chance to take this flights. All right, that was a problem. Hope you have enjoyed this problem. We are done with this lecture. Thank you very much.